Hello, welcome to today's video where we're continuing on with conic sections. Today we're finding tangents and normals to specifically the parabola and rectangular hyperbola, doing tangents and normals to the other two types of conic sections in a future video because there's a few extra different details to talk about there. So with that said, what do we need to know in order to be able to approach this? Well, ultimately, this is the beginning of a running theme for this topic, which is that ultimately, you're just going to be asked to do things that you've already done before at Maths A level, and it's just that there might sometimes be the occasional guest appearance from the formulas and things like that that you saw before in the previous conic sections video, etc, etc. And therefore today, no different. Basically, we're going to be finding tangents and normals, so you do it in the exact same way you found tangents and normals to curves at Maths A level. The only difference is things are going to potentially be more algebraic than they were in Maths A level, and that's why this stuff is further Maths A level. But really, if you can do that stuff at Maths A level, you can still do it for this stuff as well. Which is quite nice, as ultimately there are some conic sections questions which students are a bit apprehensive of because they look quite imposing with all their algebra that they're expecting you to do, and some students feel the same way about these questions, but in reality they're not as bad as they look because they are just using skills from before, but just making them appear more scary when they actually aren't. So let's launch straight into an example. We want to find the equation of the tangent to the curve xy equals 25, which hopefully you'll recognize is a rectangular hyperbola. And we're finding the tangent to the curve at the point 5t, 5 over t. So worth pointing out, that is just coordinates. It looks scary, but they are just coordinates. So ultimately, it is just the same idea of what you come across before. We need to differentiate to find the gradient of the curve, because that will also provide the gradient of the tangent at that particular point. But in order to do that, some students overcomplicate this stuff. They start applying product rule if they're a second year student, or doing things like implicit differentiation. Don't need to. We can rearrange this curve to make it y equals, which means find dy dx is super quick. It's just one of the classic times by the power, take one off the power style things. We can then find the gradient at our particular point by plugging in x equals 5t, which, although it's algebra, is just the x coordinate, and therefore we would have minus 25 over, because remember, power of minus something means it's on the bottom of a fraction, and then we've got 5t all squared. Common mistake there is, again, people don't square the 5 as well, because what we should get is 25t squared in the denominator, which means our gradient is 1 over, or rather I should say minus 1 over t squared. Okay, we've got our gradient, and we've got a point, so now we actually have already all the information we need to find the equation of the line. And the best way of doing that is y minus y1 equals mx minus x1. So in this case, we'd have y minus 5 over t equals our m, which was minus 1 over t squared, lots of x minus 5t. Now, sometimes these questions are show that questions so that you know what you're aiming for in your final answer in terms of the structure. This question didn't say, so technically they're asking for equation of the tangent. This is the equation of the tangent, and this is one of the advantages of y minus y1 equals mx minus x1. You're not wasting time simplifying it if you don't need to, particularly if you're just immediately using the equation of the curve, or line, I should say, in something like simultaneous equations later anyway. But there you go. For our own purposes, though, often what they do want is something that has been simplified. So all you'd be doing is, of course, just multiplying out the brackets. I'm going to keep that minus 1 over t squared as a coefficient of the x, if you will, but then we're going to end up with 5 over t, positive 5 over t on the other side, which therefore means if we rearrange to make it y equals, we're going to end up with this. So there you go, that's the equation of the tangent. And so therefore that is example 1 done. Something I would like to draw your attention to, though. For this first question, differentiating was very easy because it was very easy to rearrange to make it y equals, and therefore the differentiation took no time at all. But something you've got to be aware of is it's a little more fiddly for the other conic sections curves. So something to be aware of is that if you're an AS level student, you might get lucky because they might sometimes just give you the formula for dy dx for some of the conic sections curves because you don't have the knowledge needed yet to be able to differentiate it manually. However, that's only true if you're an AS level student. If you're an A level student, a second year student, you do have the skills to be able to differentiate these things. So you're expected to just go ahead and do that differentiation. And to do it, you have two main options for a lot of these conic sections curves. You can either do implicit differentiation, or you could do parametric differentiation, because the thing to remind yourselves about is, in the last video we did point out that a lot of the times in this chapter they'll give you coordinates in a question, but they're secretly parametric equations at the same time. So they have that dual role, so that's an option. So in example 2, we're now trying to find the equation of the normal to C. And a reminder, of course, a normal is perpendicular to the curve, and therefore we're going to need to differentiate to find the gradient of the curve. And you've got two different options. You could either use implicit differentiation to differentiate y squared equals 4ax. So that's what we're going to try here. Y squared would differentiate to 2y, but then multiply by dy dx if we're differentiating with respect to x. 4ax would differentiate to 4a, meaning we could get dy dx is equal to 4a divided by 2y, which could simplify to 2a over y. Therefore, that means if you wanted to find dy dx at P, then all you've got to do is plug in the coordinates into the relevant places. So it would be 2a over the y coordinate, which would be 2at, which then, of course, simplifies to 1 over t. So that's ultimately one way of finding what dy dx is. As I said, ultimately, if you're an AS student, they would have just given you a formula in the question, and you could just follow the formula. So I haven't covered that here, but obviously, if they give you a formula, just use it and be done with it. But yeah, alternatively, you're a second year student, you have an alternative way of finding dy dx, which is to realize this point P isn't just a point. These aren't just coordinates, they're parametric equations as well. The more you do conic sections, the more you get used to spotting this or just being comfortable with this idea. But if you were unsure about this being allowed, then of course you can double check and realize that these are the parametric equations for a parabola that are given in the form booklet. So it confirms that we are allowed to treat them in this way. So therefore, we're going to do it that way. Of course, x is equal to at squared. We have y is equal to 2at. So therefore, differentiating them both, we get dx over dt equals 2at. We get dy over dt equals 2a, differentiating both with respect to t. And therefore, dy over dx at the point P is equal to the dy over dt divided by dx over dt, which just gets you 1 over t. Now, interestingly, for this particular question, I would say either of these two approaches is kind of like equal in terms of usability and speed, but something you might start to see the more we get into this chapter, certainly for the harder conic sections ones, I kind of tend to prefer the parametric approach. And that's because although it looks like it was about the same working here, in reality, if I was just doing this question without trying to explain it to somebody, I wouldn't even bother to write this stuff at the top. I'd just jump straight to the derivatives, because ultimately this is just information that's already given to us in the coordinates. And so therefore, actually the parametric approach, personally, I'd say takes less writing out, because the weird thing is, because we're differentiating the parametric equations for a point, it's also telling us what dy dx is at that point as well. So we don't have to have that separate stage of plugging the coordinates in once we've found dy dx. It's just automatically the gradient straight away. So therefore, that's just a little tip. I think personally parametrics is slightly quicker, but there you go. Anyway, once you've found what the gradient is, of course, be aware this is the gradient of the curve. We want the gradient of the normal, so therefore the gradient of the normal would be, of course, the negative reciprocal of that. In other words, minus 1 divided by the gradient we've got there. So therefore that would be minus 1 divided by 1 over t, and therefore that's secretly just going to be minus t. So therefore, the equation of a line using y minus y1 is going to be y minus y1, so y minus 2at, that's our y coordinate at our point P, equals our gradient of our normal, so that's minus t, lots of x minus the x coordinate of our point, which was at squared. Again, that is already the equation of the normal, so it depends what we're doing afterwards, but often these show that questions will want you to rearrange it in the form, for instance, ax plus by equals c style form. So you want the x's and y's together on one side of the equation, anything that's not an x on the other side of the equation. So therefore you would end up multiplying up the brackets. Sorry, I'm cramming this into the bottom right hand corner of the screen. So minus tx plus at cubed, and therefore we'd get, when we've rearranged to make the tx on the left hand side and moved the 2at onto the right hand side, final answer of y plus tx equals 2at plus at cubed. Cool! That is the final answer done. The last thing I would like to highlight to you though once again is please, I beg you, use y minus y1 equals mx minus x1. With this stuff being more algebraic, students are even more liable to make silly little mistakes on this stuff, which can happen, but you'll lose more marks if you use y equals mx plus c, because at least with this, you get the equation of the line written down first, and then you're trying to do the simplification afterwards, which then means if you make a silly mistake with any of that stuff, at least you had a correct equation of the line at some point in your working. Whereas the problem is with the y equals mx plus c method, you're doing all that simplifying just to be able to get to the point where you've got an equation of any sort, because you do the simplifying before forming the equation. So therefore it is a better method just for the sake of marks to be using y minus y1 equals mx minus x1. If you're still doubting me about that, I do have a video talking about the sort of merits of that argument. So do take a look at that video. There's a link to it on the screen right now. But there you go. So that will do us for today's video. I'll see you in a future video. This one was fairly quick. And we'll be looking at some more problem solving stuff involving this chapter in future videos. Goodbye.